Hello, welcome back, Mr. Wakefield here. Looking at our first of our last four worksheet sections. Basically, they're not really sections. I'll talk about that in a minute, but they're the last four worksheet topics, I guess you could say. The first one's called the motion problems. But you can see here I've got four sections listed out here. Now, in the past, whenever we've done a video, we've had a particular section, right, that we focused on. And sometimes one section would break up into two videos, but basically it would always be a focus on a section when we did a video. This time, however, what's going on in these four sections is that these four sections have a whole bunch of different types of word problems in them with different types of themes. Okay, one of those themes is motion problems. All right, so instead of breaking it up according to section, what I do is I break it up according to theme. And so I'm going to take all the problems from these four sections combined that involve motion problems. I'm going to put it all into this one video. All of those different topics that you need to know will all be, for motion problems that is, will be in this video. That way we can focus on the theme all at once instead of focusing them by section, because I think that that's honestly a little bit confusing. Seeing all the motion problems at once, I think it's easier. So anyway, what are motion problems? And by the way, we will be doing that same thing with other themed word problems coming up in the next set of videos, where it'll say these same four sections on the top of the worksheet, but it'll be each worksheet will be a different theme. Okay, although the next worksheet will have two different videos because it's a long one. But each worksheet, though, basically has a different theme. All right, but it'll say these four sections at the top. So again, we're not doing it by section anymore. We're doing it by theme of the word problem that we're doing. So the first theme, again, is motion problems. What does that mean? It means when you have two different objects in motion. That's what we're going to be focusing on here, not just one, but two. And when we have objects in motion, whether it's a car, a train, an airplane, whatever it may be, we usually use this formula right here, and this is what we're going to be using in this section. Distance is equal to rate times time. And I wrote it down the opposite way here, but it still means the same thing. Rate times time equal to distance. But what does all that mean, though? It means that the distance that you travel when you take a trip somewhere is going to be equal to the speed. Rate is the same thing as speed here. The average speed in particular. Okay, so R is average speed, same thing as rate. Average speed multiplied by the time that it takes to make that trip. So, for example, if you have two cities that are 240 miles apart from each other, then if it takes you 4 hours to get there from one city to the other, then the average speed must be 60, because 60 times 4, the average speed times the time, has to equal to the distance traveled. And so that's why that would have to be 60 right there. Rate times time has to equal the distance. All right, now, one other thing I want to point out here is I said that it was 60 because 60 times 4 is 240 in this situation. But why did I say, why is it 60 miles per hour? I mean, we've all heard of miles per hour before. This looks like a sign you'd see on a freeway, right? Or some highway or something. What does miles per hour mean? It is actually the amount of in other words, if your car was set so that it traveled at exactly 55 miles per hour on the speedometer of the car, and it stayed that way for an entire hour, you would go exactly 55 miles. 55 miles in 1 hour. 55 miles per hour. All right. But the other thing I want to point out with that is that whenever you talk about speed, you always have per in there, the word per, P-E-R. All right. It could be miles per hour. If you live in Canada or pretty much any other country on earth besides the United States, it could be kilometers per hour, because they don't use miles. Only the United States does that. It could be kilometers per hour. It could be feet per second. All right. The point is that when you have speed, same thing as rate here, speed or rate, it's measured how? How do you write the measurement? the unit of measurement for that. It's going to be the distance measurement followed by the word per, and then the time measurement over here. So that's why sometimes it's miles per hour, sometimes it's feet per second, okay, sometimes it's kilometers per minute, all right? So here, let's say, for example, this had been 240 kilometers, you guys, just as an example. I'm changing it slightly. If this had been 240 kilometers and this had been 4 minutes, all right, then the 60 would have to be kilometers per minute. The distance component has to go first before the word per, and then the time component, which is minutes, has to go second after the word per. So if it's kilometers for the distance and minutes for the time, then the speed has to be kilometers per minute. I just want to make sure you understand how that's written, the unit of measurement for the speed. Okay, so one more time here. Suppose that this was 240 feet and 4 seconds. What would be the, how would we mention 60? Okay, how would we refer to that? It would not just be 60, it would be 60 feet per second. Okay, because if this is feet and this is seconds, that has to be feet per second. Okay, because feet is distance, just like miles and inches and yards. All right, and then time is, minutes and seconds and hours and days and that kind of thing. So that's why the seconds would go over here. Feet per second. All right, so that's how we deal with distance, rate, and time. Okay, now this is just one object we're talking about here. We're talking about a car that's traveling, from one city to another. But in this section, like I said, we're going to particularly be referring to 2 objects in motion. And there will be actually, even though it's listed as 3 here, let me pull up a clean sheet of paper here. Same worksheet here, just a clean sheet of paper. I have 3 different scenarios listed here on the worksheet, but we're actually only going to look at 2 of them. We're going to look at this one and this one. But I mentioned the second one as well because it's so similar to the first, and you could see it sometime in the future. Let's go through these 3 different situations. Let's say you have 2 objects. They could be cars, they could be trains, they could be airplanes, no matter what they are. If you have 2 objects traveling straight towards each other, in other words, they're coming from opposite directions and they're traveling opposite, meaning that this one's going to the left, this one's going to the right. They're traveling in opposite directions, but they're going towards each other, and they're going to meet here somewhere in the middle. Okay, that's what this scenario is talking about. All right, well, as it turns out, the second that they meet here in the middle, all right, the original distance that they were apart from each other, indicated with this little bracket down here, okay, that original distance apart will be equal to when you take the sum of this distance that this car traveled and the sum of this distance that this car traveled, all right, they will add up to each other. So, for example, let's say that this car traveled 10 miles and this car traveled 12, all right? Isn't it true that the original distance that they were apart from each other has to be 22? Because 10 and 12 together, it adds up to that original distance they were apart. All right? So that's something that we're going to be using here coming up. That same thing happens down here. The only difference is that you start in the middle and you go this way. And eventually it's the same thing again. If this guy's gone 10 miles this way and this guy right here goes 12 miles this way in this direction over here and he ends up over here, then what's the new distance that they are apart from each other as they go in opposite directions this way? Okay, it is 22 miles again. All right, so whether you start in the middle and go opposite ways, or if you start apart from each other and you travel towards each other, going in opposite directions but towards each other, meaning this guy's going to the left and this guy's going to the right, they're going in opposite directions but toward each other, all right? In each case, the individual distances have to add up to the total distance that they were apart from each other originally, or the total distance that they are now apart from each other because they're going away from each other in this scenario. Okay. This last one here, number 3, it says two objects start at the same time from the same point, okay, but they're going in the same direction. So the first two ones they were going in opposite directions. Now they're going in the same direction. Okay, so let's say, for example, this guy right here at the top is a little bit faster than this one. That's why his line is a little bit longer here than this line is. All right, so let's say that he's a little bit faster on top here, and eventually, let's say that he's gone 40 miles. Okay. Now let's say that at the same time that this guy reaches the 40-mile point, this guy reaches the 30-mile point. Okay. What is this little distance right here that's indicated with this bracket? Wouldn't that be equal to 10? Because the smaller amount plus the difference, we've talked about that before, smaller amount plus the difference has to equal to the bigger amount, right? You can see here that this amount right here and this amount here have to, because they're pushed together next to each other, they have to add up to this whole thing up here, because they line up perfectly. We're going to see a scenario like this as well. Okay, so let's jump into it here. It says here in the first problem, St. Louis and Portland are 2,060 miles apart. A small plane leaves Portland traveling towards St. Louis at an average speed of 90 miles per hour. Another plane leaves St. Louis at the same time, and it travels towards Portland and averaging 116 miles per hour. How long will it take them to meet? Okay, so as we always do with word problems, right? What is the question, you guys? And let's attach a variable to it while we're at it, okay, so that we can then put the variable on the problem and the equation that we create and all that. Notice that there's only one question this time, unlike the last worksheet that we looked at where it typically had two, right? And then we had two variables and we had to make two equations. Well, as we learned in the last video, it mentions up here in how to solve a word problem. In 3A here, it says if you're only trying to find one thing, you only need one equation because you're only going to have one variable. So you just need to come up with one equation and solve it, get that one variable by itself, and then you'll have your answer. Okay, that's what you do when you're only trying to find one thing. What is that thing we're trying to find? How long will it take them to meet? Since we're talking about motion problems, you guys, is that a reference to distance, speed, or time? When they say how long will it take? Isn't that time? Okay, if it had said how long is the trip, that would be distance, right? Okay, but since they said how long will it take, that's a reference to time, isn't it? I'm going to call it T for time. Be specific here, and you can call it X if you want. That's fine, just so long as you pick a letter. But be specific here. Don't just say time, because there's a lot of times in this problem, okay? The time it takes for the first airplane to go, its trip, the time it takes for the second one. But no, let's be specific here so we know exactly what's expected. It says the time before they what? How long will it take them to meet? And so it's the time before they meet. All right, so by the time they meet, how much time has elapsed, in other words? Okay, step 3. How many equations do we need, you guys? Again, since we have just one variable, we just need one equation. Now, we're going to do these motion problems along with the rest of the problems for the rest of the worksheets that we do. We're going to do it in a special way here that's going to make it a lot easier to organize your information. All right, it's with the box method, as I call it. You want to make a box here that has enough room to have 3 columns and 2 rows. 3 columns like this. There's 3 columns right there. And 2 rows like that. All right. Some of the succeeding worksheets, the boxes are going to be a little bit bigger than this, but when you're doing motion problems, 3 columns, 2 rows. Why do we have 3 columns? It's because we're going to do this right here. We're going to take that formula that I showed you earlier, just a few minutes ago, R times T equal to D, and we're going to write that across the top of the box, just like that. Okay? R times T equal to D. So the first column represents the speed or the rate, in other words. Second column is the time, and the third column is the distance. Yes, you want to write it in this order. We won't always write it in that order, but I'll explain carefully why we sometimes change it. For now, though, you want to write it in that order, okay? And I'll tell you when it changes coming up here, and we'll kind of summarize things so that you'll understand when it's like this and when it's like something else, okay? But for now, RTD. What do the two rows represent? Okay, why do we have two rows? It's because we have two different objects in motion. So whatever two objects are in motion, that each one of those two objects has its own row. Okay, the first object is the plane that leaves Portland traveling towards St. Louis. So just to make a note here, I'm going to say P to STL, meaning Portland to St. Louis, that airplane. You can even write down the word plane underneath that. All right, just you don't have to get too specific there, just as long as you know which row is which. That's what's important. What's the other object that's in motion here? The plane that left St. Louis and went towards Portland. So that means that this one is going to be St. Louis to Portland. Okay, so the first row is the Portland to St. Louis plane, and then St. Louis to Portland plane will be the second row. Here's what you do. Couple of very important things I need to tell you so that the boxes work correctly for you. First of all, if you know what a box is equal to, okay, if you know the constant number, not variable yet, but the constant number that it's equal to, you put that number in there. Okay, they gave you that information for a reason. Put it in there. So if you know the speed of the Portland to St. Louis plane, for example, you put it in there. If you know the speed of the St. Louis to Portland plane, you put it in there. Do we know those two things? We do, okay? They tell us that the speed of the Portland to St. Louis plane is 90. So I'm going to put that in there. You don't have to say miles per hour yet. We do our units of measurement typically at the end of the problem, so you can just say 90. Do we know the speed of the St. Louis to Portland plane? Yes, we do. It's 116. It tells us this right here. St. Louis traveling towards Portland is 116. Okay, so we have that. So again, if you know what a box is equal to, you know what constant number, regular number that it's equal to, you put it in there. If you don't know what a box is equal to, but you have a variable designated for it, and we don't typically make up any more variables like I mentioned in the previous video. We don't make up any more videos other than the ones that were that we came up with in steps 1 and 2. In other words, we only use variables for what? For the things that we are asked to find, in this case, the time before they meet. Okay, so don't, if you can't figure out what a box is equal to, don't just throw a different letter in there just to put something in there. Okay, the only variables you should be using are the ones we designated in steps 1 and 2. Okay, otherwise I can completely throw things off. All right, so in this middle row, in this middle column, first of all, ask yourself, do I know the time that the Portland-St. Louis plane traveled? No, I don't. It tells us the speed. It tells us how far apart the two cities are, but it doesn't tell me anything else. However, they tell us the time before they met. Okay, so I could use that. We'll just keep track of what that means here going forward. I'll explain that. But the time for the Portland-St. Louis plane before they meet is T, so I'll put that in there. Okay. Since they left at the what? At the same time, that means that the time that the other plane has been traveling in the air is the same. And so these two boxes should be the same. It doesn't mean that they'll always be equal to the variable. It just depends on the information that the problem gave to you, okay, in the paragraph up here. Okay, now, here's how it works. If the time that you put inside of the time box, whatever that is, that corresponds with the distance. So, for example, the thing that I put in here, which is T, that's the time before they met. If you put something into the box that's the time before they met, then this is the distance at the moment that they met. Since this is the time when they met, this is the distance when they met. Okay, if this was like the total distance the plane traveled all the way to St. Louis, then this would be the total, I'm sorry, if this is the total time that it took to get all the way to St. Louis, then this would be the total distance to get all the way to St. Louis. These two things correspond to each other. Okay. If this had been equal to 2 right here instead of t, then this would be the distance that it took in 2 hours. Again, they correspond, okay, to each other like that. Time and distance do. All right. Speed is kind of its own independent thing, but time and distance correspond to each other. Okay. So that means that these two boxes right here are going to be the distances traveled by the two planes when they met. Because the times that I put in these boxes are the times when they met, as it says over here. Okay. Before they met, when they met, that's the same thing. You can even change this to when if you want to, if that works better for you. It means the same thing. But do I know those distances? You might be thinking, hey, 2060 miles, that's a distance, right? Yeah, it is a distance, but that's not what you put in here. Remember, that's the total distance that the cities are apart from each other. Look at this example up here. Okay, pretend that this is St. Louis right here. Pretend that this is Portland. Let me get rid of those old numbers. Those were just examples. Okay. The total distance that the St. Louis and Portland are apart from each other is what? That's 2060. Okay. But these two boxes right here, you guys, those two boxes are what? They are, and I got it backwards there, I'll fix it. They are those two individual distances you see listed up there at the top of the page. Okay. So this distance on the right, that's this distance here because it's from Portland traveling towards St. Louis. And then this distance right here, that's this little distance right here on the left, okay, because it's St. Louis traveling towards Portland, and it says that right here, St. Louis traveling towards Portland, okay. So this little thing right here, that's this box. This thing over here on the right, that's this box. All right. And so do we know what those individual smaller distances are? They're not the big one here, 2060, but the two smaller ones. No, we don't. We also don't have a variable for it because the variable has already been used up on the time. Okay, remember, we don't invent brand new variables to go beyond just trying to answer the question. The variables only represent the questions normally. So here's what happens. If you don't know what numbers go in here, they didn't give them to you, and you don't have a variable for it, okay, you have one last option, and that's why this is great that this is the last column here. Your last option is to use this formula at the top of the box, and since it says first column times second column is equal to the third column, that means that we can multiply 90 times t to get to the third column here, and 116 times t to get to that box there. And so that's what this formula is saying. It's saying the first box times the second box, you can fill it into the third box over here in the third column. All right. So what we just found out here is that this right here, apologize, I got that backwards again. This is 116t, and this is 90t. Okay? Because again, like I mentioned earlier, these two boxes are the distances traveled by the planes at the moment that they met here in the middle. And that's why the second box is just this one, because that's how far this plane traveled at the moment that they met. It's not the total distance all the way across. It's just at the moment that they met. It's just this little distance here. Whereas the first box is this distance here. Okay? And that's why I wrote down 116t and 90t for those two little distances right there. Okay. What does all this mean now? How is this going to help us come up with an equation? Remember, that's our ultimate goal here. We just need one because we only have one variable. Well, you can see here in the picture that this distance and this distance add up to this whole thing going all the way across. So isn't it true that 116t plus 90t is equal to 2060? You can see that right in the picture, right? Okay. And so we have our equation. We only needed one, just so long as it has our variable in it, and it does. It has t in there. Okay. Now all we got to do is solve it. There's no parentheses. This is a linear equation. There's no parentheses, so we combine like terms. And since we already have a single variable term and a single constant term, okay, we're on that step where we divide out. You don't need to move any terms around this time. So we divide out, and we get t equal to 10. Put that in your calculator, you'll see that. 10 what, though? Remember, we have measurement in this problem. You got miles. You got miles per hour. Okay? We got plenty of measurement. So the answer should have measurement as well. What is the measurement? What is the word that attaches to 10 that tells you exactly what 10 means? Well, you look at what t means. T means time, right? So that means that we need to go back to the problem and look at how do they measure time in this problem. Well, it says right here miles per what? Miles per hour, right? Okay, so they're trying to tell you that the time component in this problem is hours. All right. Since it says miles per hour, they must measure the time in this problem in hours, not in minutes, not in seconds, but in hours. Okay. There are some rare cases, including one coming up, where they mention both hours and minutes. They'll mention two different units of measurement for time in the problem. I'll clear that up with you, okay? We'll talk about that carefully. But usually it'll just give you one, so there won't be any mystery. They mention hours here, so that must be how they measure time. Okay, but you're gonna, for time, what do you look for? You look for seconds, minutes, hours, days, years. Okay, those are time components, time units of measurement. Okay, whichever one they use, that's what you want to look for. Okay. Next one here. At a given hour, 2 steamboats leave a city in the same direction on a straight canal. Okay, in the same direction. Which one of these things up here is that referring to? Okay, it's going to be this one, isn't it? Because these two scenarios, again, are when the objects are going in opposite direction. One going one way, one going the other. Okay, it's just that sometimes they're going towards each other and sometimes they're going away from each other. All right, this is the only scenario where they're both going in the same direction. In this case, they're both going this way, right? Okay, so we're going to be looking at this scenario here. All right, so imagine 2 steamboats here, both at the starting line here. Not that they're in a race, but it's like that. Okay, they both start at the same time, but as you can see here, it says one of them travels at 18 miles per hour and the other one travels at 26. So one of them is faster than the other. Okay, obviously this is going to be the one that's 26 miles per hour. Okay, because it's ahead of the other one. So the fast one obviously is going to go ahead. Don't write down 18 and 26 yet. Okay, there's a little bit more to it than that, as you'll see, because these are distances. But what is 18 miles per hour and 26 miles per hour? Remember, you guys, whenever this thing that has per in it is attached to a number, they're referring to speed. So if it says miles per hour, or if it says feet per second, or if it says kilometers per minute, okay, anytime it has that per in there, that means that this is speed. So 18 is speed, and 26 likewise also is speed. Okay, these are not distances. All right. In how many hours will the boats be 26 miles apart? How many questions did they ask us this time? Once again, just like the last problem, they asked us only one question. In how many hours will they be 26 miles apart? Okay, they just want to know that one question. All right. Now, hours. It says how many hours. What is that a reference to? Distance, rate, or time? Well, because hours is a type of time, unit of measurement, they must be referring to time. Okay, so time when what? Not when they meet, like in the last problem, but time when the boats are 26 miles apart. (26 miles apart). Again, we were very specific there when we write that down so that there's no confusion on what the T means, okay? We don't want to get confused on what time they're referring to. Are they talking about the time when they eventually meet back together again? Not that they're ever going to do that because one of them's going faster. The point is, though, is that there's multiple types of speed in a lot of these problems, and so we need to be specific, as we always should be anyway. Okay. In any problem where we have two objects in motion, what do we do again? We set up this box with 3 columns and 2 rows. What are the 3 columns? R times T equal to D, just like in the last problem. And what are the 2 rows? They are the 2 objects in motion. So what I'll do is here is I'll call it faster boat. Be specific here so you don't get confused on which one's which. And I'll call this one slower boat. It doesn't matter which one's on top right there. It really doesn't. You can put slower boat as the first row. But be specific there so that you know which one's which. Okay, now what we always do, just like we did in the last problem, is we always start out of the first column and we work our way over. Second column and then finally the third column. Okay, do we know what these 2 boxes are equal to? If we do, put it in there. We do know, right? Because we know that speed is mph, right? If you see mph, that's speed, like we just talked about a minute ago. So the slower boat then must be the 18, because 18 is slower than 26. And so this one must be 26. All right. Now, how long have they been traveling? Well, it depends on what you're talking about, okay? But they only give us one reference to time, so we can use that, okay? We should usually be fine doing that if they just give us one reference to time. It says the time when the boats are 26 miles apart. So in other words, they don't tell us anything about the time. They don't say that there's 2 hours or 3 hours or 5 hours that the boats have been traveling. Okay, so they don't tell us what numbers of these are equal to like they did with the 26 and the 18. But we do have a variable that refers to time, so we could use that. That usually will be fine. We just got to be careful to understand what that means. Since they left at the same time, and I know they left at the same time because it says at a given hour. Okay, so it says that they both left at that given hour. That means that they left at the same time. That means that these 2 boxes can be the same, just like up here when they left at the same time. Okay. These left at the same time, same 2 boxes here, T and T. Okay. Again, doesn't mean it's always going to be the variable here, but these will be the same if they both left at the same time. Now, since this is the time when they're 26 miles apart, then that means that these 2 boxes right here will be the distances at the moment that they're 26 miles apart. Okay. So this smaller distance up here will be this box then. Because at the moment that they, in fact, let me write this down. This number right now that we're focusing on is 26 miles apart. 26 miles apart. Because this thing right here, this bracket, tells us how far apart they are, and they want us to focus on when it's 26 miles apart. So if this distance right here is 26, then these 2 distances right here, the big one and the small one, are what these 2 boxes are equal to, because they correspond to the T, which is the time when they're 26 miles apart. Okay, so whatever goes inside, and you don't need to make the box within the box here, all right? I'm just highlighting the fact that I'm highlighting what's supposed to go in here. All right, the distance that that the bigger one is at the moment that they're 26 miles apart must be this big thing right here, okay? And that's going to be equal to what? Well, we don't know what that distance is. We don't know what it is, but we do know And we also don't have a variable for it because we already used up the variable. But we do know, just like in the last problem, that we can multiply across. Now, don't multiply across if you know what that number is or if you have a variable for it to put in here. It's only as a last option that you multiply across. You're going to be doing it a lot because a lot of times it is the only option, but it is the last option. So if you don't know what these numbers are and you don't have a variable that you can put in there because you used it up on something else, like right here, then the only last option you have is to multiply across. Now, unlike the last problem, you guys, okay, where we added up those two boxes to get the total distance, all right, this situation is different. Let me show you why. Let's write it down in the picture. And it doesn't mean you have to draw a picture, but I'm just helping you see it better by drawing a picture. See how the bigger distance is 26t and the smaller distance is 18t? Isn't it true that these two things right here, the 18t and the 26, if you push them together, isn't it equal to this bigger thing? Because they line up, right? And so isn't it true that 26t is equal to 18t plus 26? So don't do exactly the same thing you did in the last problem, right? That's a different situation when they were going in opposite directions, okay? Here, you got to take the bigger distance equal to the smaller distance plus the distance that they are apart. That's how it works. All right. So be careful not to think that every problem is the same way. Okay, that'd be nice if it was. It'd be easier that way, but it's just not gonna, that just isn't how it works. Okay, so I've got my equation. I only need one equation with my variable in it because I only had one variable. So let's solve it. I move over the two t terms to the same side, opposite side of where the 26 is, like usual in a linear equation. Then I divide out. And I could reduce that down to 13/4, but, and again, as I promise you, I will mention this when you need to, like if it was a test question, but put your answer in decimal form. It won't do that on a homework, okay? They won't tell you how to put it, and so you can put it however you want. But on the test question, I'll make it clear, like I said before, if I want you to put it in decimal form instead of keeping it in fraction form, I'll tell you that. If I put that in a decimal form, that means I need to do 26 divided by 8 in my calculator, and I get what on my calculator? I get, should say 3.25. 3.25 what, though? What is the unit of measurement? Again, we know that t is time, and so we just need to look at how they measure time in the problem. Well, it tells us right here in the question. It says how many hours. So that tells us that they measure what? They measure the time in this problem in hours, just like the last one. It won't always be hours, but that is a very common one. Okay? So it takes 3.25 hours for these two steamboats to be 26 miles apart from each other. Okay, I'd like you to try number 3 right now. Number 3, you can see that it's very similar to the first problem, number 1, where you got two objects, two planes, again, that are a certain distance apart. They leave from their different points at the same time, and they fly what? Toward each other, just like Portland and St. Louis, all right? They flew toward each other, and there's going to be a spot where they meet. Hopefully they don't crash, right? Okay, I'm just kidding. But the point is that they meet somewhere in the middle, or maybe they'll pass each other, right? Okay, not crash, of course. And that is going to be the key part of the problem, just like with Portland and St. Louis. It says that how long will it take them to meet? Okay, same thing here. How long will it take them to meet or to pass each other? All right. So it's a very similar problem. So please go ahead and try that. And let's see how that comes out. And then we'll look at the second page. There's 3 more problems there. Okay, so hit the play button when you're done. Okay, so number 3. Two planes leave from points that are 1925 miles apart. I drew a picture here. Okay, they start out 1925 miles apart, and they fly towards each other. Okay, get you your average speeds, and then how long will it take before they meet? So the first question is time before the planes meet. Very similar to number 1 again. Step 3, we need to set up our boxes here. Okay, again, you have 3 columns, RTD. You have your 2 objects in motion that represent the 2 rows that you're going to do. All right, and you start out in the first column and you start filling stuff in, work your way over to the final column eventually, 1 column at a time. So the first column is going to be what? Do they tell us the speeds, in other words, the rates of each of these planes? Yes, they do, 225 and 325. So we put that in there. Okay. 225 obviously for the slower plane because it's a smaller speed. And then the times, again, they don't tell us anything about the times other than the time before they met is going to be your variable. So that's why I'm going to use, just like in the previous 2 problems, I use T and T, okay, for because they left at the same time. All right, it says that right here. Okay, they left at the same time. And so they're both going to be the same, T and T. And then that means that the 2 distance boxes have got to be the distance when they met. If the time column is the time when they met, which we know that is true because T represents the time when they met, then the distance column has to be the distance when they met. Each individual distance when they met. Okay, the slower plane's distance when they met each other here, okay, which is this little distance right here, that is what the first box is. That's the reason, you guys, why you do not put 1925 inside of these boxes. 1925 is not these smaller individual distances here. No, it's the entire distance all the way across. Big difference. Okay, but that's a common mistake students make, so I just wanted to make sure that you didn't make that mistake. Okay. So these 2 distances are what? They are 225T and 325T. Again, I multiplied across to fill those in because we didn't know what the distances were for these 2 smaller individual distances. Plus, we couldn't use the variable for it because we used the variable on the question, which is the time. So the only choice we had was to multiply across. Since the picture clearly indicates to us that the 2 smaller distances, when put together, is equal to the entire original distance, 1925, going all the way across, then that's why I wrote down this equation. The 2 smaller distances equal the big distance going all the way across. And here you go. So then we solve that equation. We only need 1 equation. Combine like terms. Then divide out by 550. Again, put answer in decimal form. Otherwise, you can make it into a fraction in lowest terms if I don't say that otherwise. When you get a fraction answer. And we do get a fraction just because we're dividing out, right? Okay, so put that in your calculator, make it into a decimal. That would be 3.5 exactly. And it's in hours. Okay, why is it in hours? Because we know that T represents time, and we know that time is measured in hours here because it says miles per hour. That slash means per right there, okay, if you haven't seen that before. Miles per hour. And so hours is how they measure time again. So that's the first page here. Second page, there's one more problem that's similar to the first 3, but it asks for something different this time, but what's going on in the problem with the 2 objects in motion is similar. Okay, let's take a look at that right now. It says Toledo and Cincinnati are 200 miles apart. A car leaves Toledo traveling towards Cincinnati, and another car leaves Cincinnati at the same time traveling towards Toledo. So it's very similar to problems 1 and problem 3. Okay, once again, where you've got, we'll say, Toledo right here, and we'll say Cincinnati. Again, it's optional if you want to draw pictures. I'm just writing down the pictures just to help us make it a little easier. So you've got somewhere they're going to meet up in the middle here. All right, once again. And so there's the smaller distance, or actually this is going to end up being the bigger distance, but that's not what's important. The point is that there's one distance, and then there's another distance. As they travel towards each other, there's two different distances at the point that they meet here in the middle. All right, and then there's one big distance, right? There's one big distance, okay, and that's the original distance that they were apart from each other. All right, and they tell us what that is. The original distance that they were apart from each other is 200. And then these individual distances, we can figure out with the boxes again. But there's another thing going on in this problem. It's not the same as problems 1 and 3. You'll see that here in the next sentence. It says, the car leaving Toledo averages 15 miles per hour faster than the other car, and they pass each other after 1 hour and 36 minutes. Okay? So there's a little bit of different language there, but here's the key part. What are the rates of the cars? So that's a totally different question this time. Instead of asking us for the time when they met, which they actually already told us, they said that they met after 1 hour and 36 minutes. Okay, when you pass each other, that's the same thing as meeting, right? When you meet the two cars together, it's the same thing as when they pass each other. Just depends on whether or not they stop and meet each other or if they just pass each other. But it's the same. It's going to be the same time. But they ask us for two questions here because they're talking about two cars and they ask us for the rates of the cars. So we need two different variables here, just like we had in the last video. I'll call it X and Y. Okay, what are those two things? We need to establish that first, like always. Okay, it says the rates of the cars. So we need to know the rate, in other words, the speed of the first car and the rate of the second car. But let's be even more specific than that so that there's no confusion. Which one is the first car? First car is the one that left Toledo. They leave at the same time, but I'm just talking about what they mentioned first here. The rate of the what? The car that left Toledo and it went towards Cincinnati. So I'll call it T going to C. Toledo to Cincinnati car. And then the other car is what? It's the one that left Cincinnati traveling towards Toledo. So I'll call that C going towards T. Like that. Okay. And step 3. How many equations am I going to need this time? I'm going to need 2 of them because I have 2 variables, right? So we're back to finding 2 equations because we have 2 variables. But the box setup is still the same. You're still going to do RTD across the top. And you're still going to do the 2 rows because you have 2 objects in motion. What are those 2 objects? Just so that we should label them so we don't get mixed up. All right, those 2 objects in motion are the Toledo to Cincinnati car and the Cincinnati to Toledo car. Okay. So I labeled them so that way I know which one's which. Okay, now, do they tell us what the rates or the speeds are? No, actually they don't this time. They do tell us that one of them is faster than the other by 15. That does not mean that they're equal to 15, though. Okay. For example, if I told you that I'm going 15 miles per hour faster than you, does that mean that you and I are going 15? No, of course not. Does it mean that one of us is going 15? No. It just means that one of us, whatever we're going, is 15 faster than the other one. That's all that it means. So you don't put 15 in here necessarily, okay? You need to put the actual speeds in here. Let me give you an example, okay? If I'm going 15 faster than you, and let's say I'm going 60, aren't you going 45? You see how there's no 15 in there. It's just telling you the difference between the numbers. Okay, you need to put the actual speeds in there, though. Okay, yes, they could have been 60 and 45, but since I just made those numbers up, that's not what we're going to put in there. In reality, we don't know what the speeds are. They just tell us the difference between them, 15. So here's the thing, though. like I've been telling you all along here in this video, if you know what a box is equal to, put that number in there. If you don't know what a box is equal to, but you have a variable for it, and you can see here that we do have a variable for the rates of these two cars here, X and Y, then that's what you put in there. That's what you put in there. X for TC and Y for CT, and that's why I put it in that order. Do we know the times that they've been traveling? Actually, this time we do. Okay, it says that they pass each other after 1 hour and 36 minutes. So again, at the moment that they meet, we know what they make a reference to the time at the moment that they meet. It's just that unlike on the first page, unlike the first three problems, okay, it's not a variable this time for when they meet. They actually tell us what it's equal to. It's not something we have to figure out. Now, how do I write 1 hour and 36 minutes? That's two different units of time measurement there. When they give you hours and minutes both, what you got to do is you either got to convert it all the hours only or all the minutes only. Okay. Now, in this case, you must convert it to hours. Let me tell you why. Since the speed is measured in hours, miles per hour in particular, since they use hours within the speed component here, then the time has to be in hours. Okay, you can't have miles per hour and then have the time be in minutes. It's not a match. Okay, it has to match up. So if this had been feet per second, for example, then your time would have to be in seconds. If this was miles per minute, then this would have to be minutes. Okay, it has to match up. Since this is miles per hour, this has to be hours. So how do I convert this to being just hours only? Well, here's how it works. If they give you 1 hour and 36 minutes, that's the same thing as 1 and 36/60 hours. For example, if it had been 1 hour and 10 minutes, then it would be 1 and 10/60. If it had been 1 hour and 15 minutes, it would be 1 and 15/60. Why the 60? It's because there's 60 minutes in an hour. Now, mixed numbers are no fun to put inside of an equation. In fact, we never really do that. We always convert it to a fraction or decimal. This one I'm going to convert to a decimal. And the way you convert a mixed number to a decimal is by putting this fraction into your calculator. Okay, what is that going to be equal to? What's 36 divided by 60? It is equal to 0.6, which is the same thing as just 0.6. So what you do is you bring down the 1, and now you have 1.6 hours. Okay, so you convert the fraction, and then the 1 just comes down with it. Okay, so don't say 0.6. That'll get all mixed up in there in the middle. Just say 0.6, and then attach the 1 to the front of it. And so the two objects have been in motion for 1.6 hours, because that's the same thing as this thing that I circled here. And once again, you guys, just like I said before, all right, this smaller distance right here is going to be this distance here, because the time is the time at the moment that they met, 1 hour and 36 minutes, 1.6. And so therefore the distance here is the distance when they met. That's this little amount, okay, that you have at the moment that they meet here in the middle. This is the distance that the Toledo to Cincinnati car has traveled. And so that will go here. The distance for the other car, which is this small distance right here, at the moment that they met in the middle, okay, it's going to be this amount, and so it's going to be whatever goes in here. And once again, we don't know anything about the distances, the individual distances, that is, we only know the total distance all the way across, not the same thing. We also can't put a variable in here because we already used up our variables on the rates. So again, the only option we have is to multiply across. And like I said earlier on this problem where the two objects travel towards each other and they eventually meet in the middle, okay, at the moment that they meet, these two individual distances have to add up to the total distance all the way across. And so this is what? This is 1.6x. This is 1.6y, and so what's our equation going to be? It's going to be 1.6x plus 1.6y is equal to the whole thing all the way across, 200. Let's write that down. Okay, here's the problem though. We need two equations. This is a perfectly legitimate equation, but we need another one because it is got two variables. Okay. Now, look at this sentence right here. Sometimes, here's the thing. In most of these box problems, you don't have to go back to the words to find another equation, but in this one you do. Okay? We cannot come up with any more equations from this box here. All right? We knew that we could add these two things together to equal the total distance all the way across, but that's pretty much all that we can do. At least in a problem like this with this type of scenario where they're going towards each other. Okay. So we need to go back to the problem, and here's where this statement comes into play right here. Okay. If one car is 15 miles per hour faster than another, and it doesn't matter what the number is, if one car is faster than another, what does that mean in terms of an equation? Let's write that down. If one car is faster than another, it means that the speed is more than, let me write that down, 15 more than the other speed. So the first speed, the speed of the first car, in other words, the first speed is 15 more than the other speed. If I said to you right now that my car is 20 miles per hour faster than, is traveling 20 miles per hour faster than yours, there's no equal sign in that statement. My car travels 20 miles per hour faster than yours. Okay, see how there's no is? The word is not in there. Nothing that represents an equal sign. Okay, same thing in this statement. There's no is in there. There's no equal sign. But see how I rewrote the problem so that the word is in there? Okay, when somebody is faster than somebody else, that means that their speed is more than the other speed. And so we can make a equation out of this by recognizing that is means equal, more than means plus, okay? And so we can just translate it right off of this sentence. The first speed, which is the one that, because the first thing they mentioned here was the one that was leaving Toledo, so that's the TC car. That speed or rate is going to be X. Okay, so they're saying here that the car leaving Toledo, that first speed, right, the speed of that car, which is X, is, that's equal. So we got what here? We've got the first speed, which is X. Okay, that's X. Equals what? 15 plus the other speed. Equals 15 plus the other speed. What's the other speed? That's the speed of the other car, which is Y. And there you go. So there's your second equation. So again, if something is faster than something else, you can rewrite that statement to have an equal sign in it by saying that the first speed is more than the other one because it's faster than. Okay. All right. So we now have two equations. And so therefore I can do what I did in the last video. You can either use substitution or elimination. Since the x is already by itself, I'm just going to use substitution here. I'm going to plug in 15 plus y into the other equation. Then I solve that equation. So I need to distribute out the parentheses first. Calculator will definitely help you out here, especially with these decimals. 24 plus 1.6y, and then the rest. Combine like terms. and then move over the, subtract the 24 over with the 200. If I subtract that 24 over, I get 200 minus 24 is equal to 176. And by the way, when you have a decimal inside your fraction and you're on that step where you have gotten the variable by itself and you just have a couple numbers here, one on top, one on the bottom, if one of them's a decimal, that automatically means to unless I indicate otherwise, to make that into a decimal answer. Okay, or at least put it in your calculator. It might come out as a whole number. But what do we always do when we try to make it into a decimal answer? We put it in our calculator, right? So if one of these two numbers is a decimal, just put it in your calculator. Don't try to put that lowest terms. We never do that when we have decimals in our fractions, right? So that should automatically tell you, oh, I need to put that in my calculator. Okay, just like you would if you were making it into a decimal answer. On your calculator, what do you get? 176 divided by 3.2. That's exactly equal to 55. I still got to solve for the other variable though. So I go back and I plug that in. And so I get x is equal to 70. So what's the final answer? Well, as I mentioned back in the previous video, I'll write it down over here. When you have to find two things, not only do you have to say how it's measured, but you got to tell me which one's which so that there's no confusion. The y and the x are both rates, and rates are measured with miles per hour in this problem. Remember, rate is speed, and speed, okay, the way to find out how speed is measured is to look for that per. Okay, miles per hour. Oh, okay. Since this is where the per is, that must be how they measure speed. So this is miles per hour. This is also miles per hour. But which one is which here? Which one of these is the Toledo to Cincinnati car? Okay, well, we go back to our variables. Since x was the 70 and since x was the Toledo to Cincinnati, that must mean that the Toledo to Cincinnati car is the 70 miles per hour. Okay? And then, so therefore the 55 is the y. That must be the Cincinnati to Toledo car. So again, tell me which one's which there. All right. So 70 goes with Toledo, Cincinnati. 55 goes with Cincinnati to Toledo. All right. Okay. So that is what happens when two objects are traveling towards each other. And we also saw when they both are going in the same direction, starting from the same point. That was problem number 2. These last two problems, you guys, are a bit different. Okay, this is when you actually have one object, but it feels like it's two. It feels like they're talking about two objects because it's in two different situations. It involves a boat. Okay, and let me draw you a picture here. Okay, if you've got a boat and you throw that boat into a river, okay, every river has what we call a current. It's what makes the river have waves, okay, and that current always goes in the same direction that the waves are going. Okay, that's what makes the waves go that direction. But it has a certain speed to it, okay, and the faster the speed, the faster the waves are going. Okay, which means that the faster your boat's going to go, okay, if you throw the boat into the water so that it'll go in the same direction. We'll get into that in a minute here. So let's say that your current is going 3 miles per hour, okay, and let's say you throw your boat in the river, and let's say that you have one of those motors on your boat. It's like a little motorized boat. And let's say that boat normally has, its engine that it has normally is strong enough to have that boat go 10 miles per hour if there was no current. In other words, if you were in a lake and there was no current, it was just a nice still lake, okay, that boat would normally go 10 miles per hour with that engine, okay? And now all of a sudden you've taken that boat that normally goes 10 miles per hour in still water, and you throw it in this river. How fast do you think that the boat will now go if you turn on the engine and you have it going in the same direction as the current? It's now going to go 13 miles per hour. How did I figure that out? Well, you could probably tell that I added these two numbers, right? So if you put the boat in the river with the current so that it's going in the same direction that the current is going in, then you add the speed of the current itself to the normal speed of the boat if there was no current. Now let's say, for example, that I've gone down the river for a little while and now I need to turn back around and go back to where I started. Okay. What's going to happen? What's going to happen is you're going to be going against the current, right? Isn't that going to slow you down? Yes, it is. How fast do you think you'll be going now? Well, you'll be going 7 miles per hour. How did I figure that out? 10 minus 3. Okay. So that's how it works. Okay. Now we have names for this. Okay. When you're going with the current, if you throw your boat in the water and you're going with the current in the same direction, that's called downstream because it makes you feel like you're going downhill. It's kind of like when you're riding your bicycle downhill. Okay, the gravity of going downhill speeds you up, right? Just like the current speeds you up when you're in the river. So they call it downstream. It doesn't mean that the river literally is going down, okay? It just feels like it's going down. And then when you're going against the current, that's called upstream because it makes you feel like you're going uphill. Okay? So downstream is what? With the current. You'll see that in one of your homework problems. It'll say, instead of saying downstream, it'll say with the current. So now you know that it means the same thing. And in that same homework problem, it'll say against the current. Against the current is the same thing as upstream. So please make a note of that because we're going to be talking about downstream and upstream. That's the language I'm going to use here is downstream, upstream. So I want to make sure you know that it means the same thing as these two phrases right here that I wrote down. Okay. Speaking of downstream and upstream, we have a special pair of formulas that we use for downstream and upstream problems. Okay. And this involves the downstream speed. In other words, how fast is your boat going? Okay. When you're going downstream, how fast is it when you're going upstream? It's just the same exact thing that I just said, though. I just wrote it down with words. That's all. Okay. As I just mentioned a moment ago, if you've got a boat that normally goes 10 and you throw it into a river with a current of 3, what this is saying here is it's saying that the downstream speed will now be the still water speed, which is 10, plus the speed of the current, which is 3. So the downstream speed would be 10 plus 3. All right. And then the upstream speed, as I mentioned, it's going to slow you down when you're going upstream. So it's going to be what? 10 minus 3. That's why the upstream has the minus. It's because it slows you down. But the downstream has the plus. It's because it speeds you up. Okay. Now, when we actually do these problems, you guys, you're going to have variables in here. So I wanted to make sure to show you the simpler example first, even though this is not an actual problem that we're going to be doing, so that you'll understand these formulas, how they work better. But we're now going to have variables going in here. And where the variables go is not always going to be in the same place. Please understand that, okay? A lot of people think that the variable always goes in the same part of the formula. It doesn't. It just depends on what the variable represents. What does the variable always represent, you guys? What we're trying to find, what the question is, right? Okay, so it all depends on what the question is. Let's try this. Number 5. A river has a current of 4 kilometers per hour. So it's just like that example I showed you, only instead of it being 3, it's 4. And also it's kilometers per hour, not miles per hour. Find the speed of Lynn's boat in still water. Okay, so in other words, what's the normal speed that the boat would go if there was no current? That's the question. If it goes 40 kilometers downstream in the same time that it takes to go 24 kilometers upstream. Okay, so what's the question? There is only one question this time. It says find the speed of Lynn's boat what? In still water. Remember, you guys, in these downstream, upstream problems, there are 4 different types of speed. And so we really got to be specific here. You do not want to say X is equal to speed. That's not enough because there's 4 different types of speed. How do we know which one it is unless we're specific here and we're certain about it and we read our problem carefully to find out? We can see here that it's speed and still water that they want us to find. Okay. Don't write down the boxes yet. We're going to change up the box setup slightly here. It's still going to have 3 rows and 2 columns, so you can write that part of it. Okay. But what goes on the outside of the boxes is a little different. First of all, when you have a downstream upstream problem, the 2 rows are the downstream row and the upstream row. There's not 2 different objects this time. There's one object, it's the boat, but it's in 2 different scenarios. One where they're going downstream, one when they're going upstream. So that's why you still need 2 different rows, 2 different situations. Now, here's the thing. On the top, you guys, we're not going to do RTD this time. I'll explain why in a second, but let me, actually, I'll explain now. The reason why we always wanted RTD in the past problems is because, remember, the distance column was the one where you didn't know what it was equal to, and so the only way you could fill it in was to multiply across to fill it in, right? Well, in these problems, in the downstream upstream problems, the thing that you always, the one thing that you don't know this time is not the distance. I'll tell you, you'll see. In fact, they tell us the distances. They say 40 kilometers and 24 kilometers. So we know the distance this time. We even know the rates, okay? And that's what these formulas are for. They're going to help us figure that out. But it's the time, you guys, that we don't know. It's the time. So we need to reconfigure this formula. It still has to come from this formula, what we're going to end up using here. It still has to come from this formula, but T has to be over here. Well, you can't just rearrange the letters however you want. That's not how math works, okay? We can't be all creative about it. Okay, we have to obey mathematical rules and stuff. So let me take a look at this formula. Let me write it down on the scratch sheet of paper here. Let's get T by itself. And we learned how to do that in the last section of the previous worksheet packet. Where if you've got, in fact, I'll pull that out here for you. The last section of the worksheet packet that we just finished previously. Here it is. Okay. When you're trying to solve for a variable, and in this case I want to get T by itself, so I'm just trying to solve for T. Okay, what did we do when we had a single term on each side? One side has the variable you're trying to get by itself, and one side doesn't. You divide out, right? Same thing here. All right? You divide out, because one side has the T, one side doesn't, but there's a single term on each side, so you divide out. I divide by R to get the T by itself, right? So what do I end up with? T is equal to D divided by R. That's what we're going to use. Let me show you. Since I want the T over here on the right, here's what I do. D divided by R equal to T. Okay, so let's sum up here. When you're doing an upstream downstream problem, you guys, use this formula because you want the T to be in the last column. Okay? The only thing they tell us about the times is that they're the same, but they don't tell us what the times are. They don't allow us to use a variable for the times because we have to use the variables on the question, which is the speed and still water. So we don't know what the times are. We can't use a variable there. And so the only thing that we can do is to go across to fill in these boxes. We'll get to that step here in just a moment. Okay, so use this formula across the top in this order with the division symbol. It's not multiplication like this was here. It's division because this formula I just did figured that out. But in the other problems where you have two objects in motion and you're doing the boxes and everything, then you use RTD. It's just in the downstream, upstream problems that you want to reverse it around. Okay? Let me know if you have any questions about that. Okay, let's get started. We always start with the first column and we work our way over. First column is the distance downstream and the distance upstream. Distance downstream, distance upstream. Matching up the boxes with the words here, or in this case, the letters. All right, this is distance, so up here. So what is the distance downstream? 40, right? It tells us that right there, 40 kilometers downstream. Kilometers is distance. It doesn't say kilometers per hour, it says kilometers. Okay. 24 kilometers upstream, so this must be 24. Okay, how do you do the rate in a upstream downstream problem? That's where this formula comes in down, or these formulas down here. Still water plus current, still water minus current. That's the downstream speed and the upstream speed. Remember, you guys, these two boxes right here are the downstream speed and the upstream speed. Okay, so they are always going to be equal to these two things together. Still water plus current, still water minus current. Those two things are equal to the two boxes. These are the two boxes right here. Okay? And so therefore we need to put these two things in the boxes, okay, because they're equal to these two things. All right. So actually, I should have drawn a box around these two things. This is what's actually going to go in the box, you guys. These two things are going to go inside those two boxes. Where it says R, okay, where it says R, you're going to put these two things in there. What is still water plus current? Again, do we know what the still water speed is? No, we don't, but we have a variable for it. We have a variable for it. It is X. And so we use that. Okay, but we still got to say plus the current. Do we know what the current is? The speed of the current, I mean. Yes, it's 4. Okay, so this must be X plus 4. Okay, X plus 4. I'm just following this whole thing here. That's equal to the downstream speed, which is what that box is. Upstream speed, still water minus current. It's exactly the same as this one. It's just that the plus changes to a minus. So instead of X plus 4, it's going to be X minus 4. Okay? Now, we don't know anything about the times other than the fact that they're the same. I'll get to that in a minute. But because we don't know anything about them and we don't have a variable for them, okay, the only thing we can do is go across. And since this says divide, we're going to say 40 divided by X plus 4, not times X plus 4. And we're going to say 24 divided by X minus 4. And so we filled in the boxes. Here's the key thing. What does same mean, you guys? Same means equal, right? That means that these two boxes are equal to each other because these are the two times. It says the same time, so they've got to be equal. Let's make them equal to each other. That creates an equation, doesn't it? When two things are equal to each other. All right? By the way, you guys, if you're desperate to come up with an equation, you can't just make up an equation where two sides are completely identical. Like, for example, you can't say x times 1.6 is equal to 1.6x. Okay? See how the two sides are completely identical here? If I simplify this, if I multiply that out, I would get 1.6x equal to 1.6x. That's called an identity where the two sides are completely identical. Okay? These two sides are not identical. But we know that they're equal because of what we figured out. We talked about, the picture and everything that we drew. Okay, so we know that these things are equal, but they are not identical. You can't just come up with an equation that's identical on both sides and say, hey, there's my equation. I did it. I came up with an equation like I'm supposed to. Unfortunately, identities are not going to count. That's not going to help you. That's not going to get you to the answer. I just want to remind you of that, all right? That's something I always remind my students of when we're doing word problems, okay? Make sure that you don't just come up with two things that are completely identical looking like this, okay? But that's not the case here. All right, these are not identical, but we know that they are equal because of this phrase right here. Okay. I only need one equation because I have only one variable, right? And so that's all I need here. I just need to solve this. And as we learned back at the beginning of this worksheet packet, the very first worksheet of the packet, if you have an equation with just a single fraction on each side, you can not cross cancel, but cross multiply like this. Put brackets around those two denominators because they got more than one term in it, and you're multiplying them by the opposite numerator. And now let's solve that. So I distributed. There's no like terms to combine, but I can move over the x's to one side. And I'm also allowed to move these over at the same time. And I get what here? I get 16x is equal to 256. It's now time to divide out on this linear equation. 256 divided by 16 is equal to, if you put that in lowest terms, it does divide evenly, so part of putting it in lowest terms is to divide it straight up if it divides evenly, and your calculator will tell you that it does because your calculator gives you a whole number answer of 16. Okay, so 16 it is. 16 what though? Again, to figure out the unit of measurement, we recognize that the variable represents speed, so how is speed measured in this problem? If we go up here to the top, we can see that, again, anytime it says the word per, all right, you take the thing just before the word per and the thing just after, all right, and all that together is your unit of measurement, okay? Kilometers per hour. In other words, the distance component should be just before the word per, and the time component should be just after it, kilometers per hour. So that's how I knew that that was the time unit of measurement. I'm sorry, the speed unit of measurement. Okay, kilometers per hour. Okay, this next one here is very similar. The difference, though, is that it doesn't ask for the still water speed this time. It asks for the speed of the current. So what does that mean? Okay, and this is what a lot of students, because they're not being careful, so we need to be careful here. A lot of students not being careful, they don't recognize this sometimes, all right? So listen up here. Because they're asking for something different, that means that your variable is going to go here. It's not going to go over here like it did in the last problem. It's going to go here because the variable is what? It represents what you're asked for, the question in the problem. All right, so since the question is the speed of the current, the variable should go here. All right. So just wanted to give you a heads up on that. Okay. But otherwise, the problem is very similar. Go ahead and try it. Hit the play button after that, and then we'll wrap things up here. Okay. How I can travel 8 miles upstream at the same time you can travel 12 going downstream. So again, it gives you the two different distances, one for upstream, one for downstream. His boat goes 50 miles per hour in still water. So that's the speed, miles per hour, in still water. What is the rate or speed of the current? I mentioned that here. Attach a variable to it. Since it's a downstream upstream problem, I use that same formula that we did in number 5, as we always do in a downstream upstream problem. Okay, what is the distances for downstream and upstream? They are 12 and 8, right? Make sure not to get those backwards. 12 for down, 8 for up. What are the rates? Well, remember, the rates for down is still water plus current. For up, it's still water minus current. But remember, okay, this time they tell us what the still water speed is. It's 15. Okay, so for downstream, it's going to be 15 plus x. Okay, because remember, downstream has got the plus in it. But you always got to put the still water first, you guys. Believe me, the ants will get all messed up if you don't put that still water first. So the 15's got to go first since that's the still water speed, and then the current, the speed of the current has to go second. You might be thinking, hey, but wait a second, isn't x plus 15 the same thing as 15 plus x? Yes, it is, but here's the problem. X minus 15 is not the same thing as 15 minus x. That's why I say you got to put the still water thing first, the still water speed first, and then the speed of the current second. Otherwise, this will get it all messed up because it'll be x minus 15, and then you'll get the complete wrong answer. Believe me, you will. So, still water speed first, speed of the current second. Since x is the speed of the current, that's why it goes second. We then, because we have no choice, we have to divide across. Okay? Again, divide, not multiply, because the formula tells us that. Okay? The only thing it tells us about the times in this problem is that they are the same time. So the only choice I had was to go across. Since it says same time, though, that means that these two things, again, are equal to each other, which leads to this equation right here. Those two boxes are equal to each other. We then solve that equation. We only needed one equation because we only have one variable. So you cross multiply because each side is a single fraction, as we learned in the first worksheet of this packet. We then distribute and continue solving here. Move over the x's to one side, move over the constant numbers to the other side. Okay. Your equation might say negative 20x on this side and negative 60 on the other side. It's going to be the same answer, so don't worry. And what is that answer when we divide out? That's going to be x equal to 3. 60 divided by 20 is 3. Okay. 3 what? Well, again, x is speed. Speed is measured how? It's measured miles per hour. You can see that right there. So the final answer is 3 miles per hour. Okay. There we go. So that's motion problems, you guys. All right, one more thing before we stop the video. There is one homework problem, just one, where they talk about something that's very similar to downstream, upstream, but it's not. But it works the same way. See number 21 right here? It talks about an airplane flying in wind. Okay? When an airplane flies in wind, it's similar to when a boat gets into a river with current. Okay? If you're flying with the wind, just like when you're going with the current, all right, that's the same thing as downstream. When you are flying against the wind, as you can see right here at the end of the problem, that's the same thing as upstream. So I want you to, when you do this problem, I want you to treat the 500 miles like it's the downstream distance, the 400 miles like it's the upstream distance. And then notice it says the wind is blowing at 25 miles per hour. That's the same thing as current. So the speed of the current is 25. We call it the speed of the wind here, but I'm just saying that it's the same thing. It works the same way as the speed of the current in the problems that we just did. Okay, so keep that in mind when you do that problem. There's just one problem like that. The other two problems I'm going to assign involving downstream, upstream will actually say, they'll actually involve a boat and not a airplane. So you'll be fine there. We've talked about that. So that concludes motion problems. Again, let me know if you have any questions about that as we move forward here. But otherwise, take care. Have a great day. And we'll see you back for the next video, which is in what we call mixture problems. Okay? So we'll see you back there at that time.